Video of CFD from scratch. Previous videos we discussed the governing equations, pressure, the finite volume formulation, and here we're going to implement the equations for a lid-driven cavity in Python. This full notebook that includes all of the details are available in the links for this video. As a summary, we had the following equations that we developed as part of the numerical finite volume solution. We have the U momentum equation given here in blue. du dt is h minus delta p over delta x, where h is given in this quantity here. And all of these phase properties are written in this big blue chunk. So this is the equation with the supporting cast. We have a similar equation for the V momentum equation with its supporting cast. And then the continuity equation is this pressure equation, which has the form of an AX equals B system, where the coefficients of P and the right-hand side B are summarized in these two tables. So these are the things that we need to code. For the lid-driven cavity, again, this is a box with sliding walls, and we don't have any flow. The normal component of velocity through the walls is 0, and the tangential component can be specified. So we'll begin with the little boilerplate, Python boilerplate. We'll need NumPy, and for the AX equals B system, we'll use a sparse matrix. Most of the matrix will be zeros, so we'll include some sparse functions there, and then plotting package, and finally this np.ix is stored as ij for convenience, and we'll discuss that in a few minutes. So the first thing we do, we're setting a function here, and for convenience writing these a number of these variables as globals so that they can be seen by other variables. But we set these user specifications, so we specify our grid to have 40 grid points in X, and in this case 60 grid points in Y. And the size of the domain, Lx is 1 and Ly is 1.5. And we set the kinematic viscosity, and then boundary conditions. The UBC on the top, bottom, right, and left. So the U velocity on the top and bottom, and the V velocity on the right and left. Now, we also specify how long we want to run for, but we write that in terms of a characteristic box timescale. So this is n tau run is 2, and we'll run for 2 characteristic box times. And then the CFL is a time step size factor. If we make that too high, then the code becomes unstable, so keep it relatively low. So these are the things that the user changes, and then we're going to, using those, we're going to set up our computational grid, our time values, and initialize our domain variables. So the X grid is simply a linear spacing of points, nx points from 0 to Lx, similarly for Y, and then dx and dy are just differences between the grid values. The box timescale, here I'm using the average of the domain lengths and then dividing that by the maximum velocity. So if we had a square grid and we were only moving the lid, then this would be the box edge divided by the lid speed gives you how long does it take for the lid to make one sweep across the box. And then the runtime will simply be that quantity times the number of times we want to do that. The corresponding time step size will be equal to this. We'll evaluate the time step size as the CFL, this time step factor, multiplied by the smallest grid size, because we want delta t to be as small as it. Want it to be conservative, so we want to take the minimum value. So the smallest grid size and the largest box velocity, because that should be the largest velocity that is found in the domain. Now that we have the delta t, the number of time steps is just the runtime divided by dt, but that won't be an integer, so we force it to be an integer. And then we recalculate delta t based on the runtime and the number of time steps, just to force consistency between having an integer number of time steps and a delta t that fits in t end with those time steps. Okay, and then we initialize a grid of u velocities, a grid of v velocities, and a grid of pressures. So technically this p is p hat. Now, the size of our u and v grid is nx plus 1 and ny plus 1. So we added plus 1 because in our grid, when we shift it, we move down and we'll add another point so that there's a point on the right boundary, and similarly for y. So in this case, the picture shows a 5 by 4 grid, and nx plus 1 by ny. And then in the v direction, it will be similar. Okay, so the u momentum equation, encoding this, we're going to use array slices to try to avoid loops, and that improves both the speed and makes the code easier to read, arguably. And here is where we're going to first use this ij as np.ix for certain array slices. So we're solving it on this grid, and the u array depends on this hu. So first thing we need to do is have a function to compute this hu quantity. That is, in solving the u momentum equation and v momentum equation, basically we want a function that gives us hu, and then hu combined with pressure will allow us to time advance the momentum equation, similarly for v. And we'll do the time advancement with a simple explicit Euler method. So here's what our hu function looks like. We need all of those phase quantities, so we first make space for them. And all of these phase quantities are on the u grid, and so they have nx plus 1 by ny. You get to make choices about whether you want to include nx plus 1 or just nx minus 1. Here, we're going to actually, we're only going to solve the interior velocities. So here we have velocities on the edges. We're only actually solving for these, but we make our matrix include all of them, even though we only update the interior values. And that's convenient for evaluating phase quantities, because that means that we don't have to treat this cell special. If we want to find this phase, we have this value in the matrix without having to explicitly compute it. That might be desirable in certain circumstances if we wanted to generalize our matrix, but for us, we'll make our arrays include all of these blue arrows, but we'll only be updating the interior values, and similarly for y. So all those phase values have a matrix of nx plus 1 by ny, and we have all these quantities. Now we're going to use this index notation, or this array slicing in Python. So we have I is np.arange 1 to nx, and that will be 1 to nx are these three in I. And then for the y directions, we'll sometimes use all of them and sometimes use these three, and then depending on what we need to do with the boundaries. So to calculate the east, it's simply all the I value, the interior I values, and all of the j values are just the two neighbors, and the west are the two neighbors. So this one's pretty straightforward. When we look at u north, when we deal with u on the north face, sometimes it's this boundary velocity, the lid velocity. So we want to deal with all of these cells, these 9 cells in the picture, and then we'll treat this cell later when we're dealing with the north faces. So when dealing with the north face, we'll treat these cells and then the top row separately, and that's what we're doing here. So j goes from 0 to ny minus 1, and we calculate we interpolate the north faces. And then we say, okay, the last cell at the top is simply the known boundary value. The north face is just the lid velocity. And similarly for the bottom, when dealing with the bottom, we have these 9 cells that are normal, and then this bottom row needs its south face is the bottom velocity. So we do those in 2 steps. Similarly for V north, so for V north we just get V north and V south, so we can get the full range of J. And you're welcome to go through this. I won't list every detail, but you're welcome to go through and look at what these array slices are and how they relate to this grid. So when we're looking for V on the north is always going to be for a given U cell. V on the north will be an interpolation between V values which are above the circles. So you've got a V cell there and a V cell there, V cell here, V cell here. And in the V grid, you actually have values on these top faces just like you have values on the right for the U grid. So they're present, and you don't need to do any special treatment if you're next to the edge. And that's why all the V north cells can be done in one shot, and all the V south can be done in one shot. Now for the taus, we have something similar. We have the finite difference for the tau xx east, tau xx west. And then when we're dealing with tau xy north and south, depending on where we are, if we're looking at this cell, if we're looking for these interior cells, we need a value at the face, we can central difference it. But if we're on the top row, for example, and we need the tau on the face, that's a derivative at that face, and we need to use a one-sided difference there. So in that case, we'll go lid velocity minus cell divided by half a cell spacing, and that's what we have right here when you see half a cell spacing and the top lid velocity minus the cell. So we have a little bit of special treatment there depending on what needs to be done. In our domain, this quantity here, because we're at the top of the grid and the velocity is 0, this quantity technically is 0, and you could replace it with 0 if you wanted to. Similarly for the south values. Once we've computed all these face values and we have space for HU, we can fill it in, and we literally just type the code that we had for that's HU. And so we code that thing in UU, UW, UW, etc. And that's what we got. This IJ, this capital I, capital J, which is aliased for np.ix underscore, that's needed because when we make array slices that are partial slices, we just need to tell Python to expand that into the full square or rectangular patch. It doesn't automatically do that for us. If we're dealing with all of the cells in a given direction, then we don't need the IJ, but you can look up the documentation for those details. Okay, so the V momentum equation is the same story, so I won't discuss that. Okay, now when we're dealing with the pressure solver, we have an algebraic equation for each grid cell. We have a pressure at each grid cell, and we have an equation for every grid cell. So we need to set up that AX equals B system. But in solving a linear system, the unknowns, in this case P hat, need to be a linear array, a one-dimensional array. So we have a two-dimensional grid. We need to turn that into a one-dimensional array. And we do that simply by reordering our grid points. So we'll loop along X. So we'll write this as 0.0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 when setting up that system. Now before, we saw that we had 9 equation types, an interior, 4 sides, and 4 corners. And the code below parallels the tables that were shown with those equations. So for every grid point, we're going to have 4 matrices for the neighbors. So for every grid point, we have 5 matrices. The base coefficient, and then the 4 neighbors. And we have that for every grid cell. So we really have 5 coefficient matrices and a B matrix. And then we're going to arrange those into this A P hat equals B system so that we can then solve it. So let's go through and just recap with the notes here. Each cell has a P hat coefficient for itself and 4 neighbors, and this gives an NX by NY matrix, basically, array, 2-dimensional array for the base point and each of the 4 neighbors. And similarly, we have an NX by NY array for B. So we have 5 coefficient arrays and 1 B array. Once the P coefficient and B arrays are set, we need to reorder them from the 2D arrays into a 1D array. And we tile the points as indicated in the grid above, counting the X direction and from low to high in the Y direction. And we reshape that using NumPy's reshape function. Now, since we're numbering along X, and X varies along columns in our arrays, meaning when we write U, we write UIJ, but that implies that I is columns in the matrix, whereas I is horizontal in the way that we visualize our grid. That means that when tiling this, we are actually using a so-called column major ordering, and that's what's done in Fortran. Python defaults to using row major ordering, so we just need to specify order equals F when doing the reshape function. And you'll see that below. So for incompressible flows, pressure is only determined up to an additive constant. So we had grad P in the governing equations, which means P plus any constant is still the same as grad P without the constant, because gradient of constant is 0. So only pressure differences matter. And so what we're going to do to keep the pressure from drifting, the absolute pressure from getting too high or too low, at the end of the pressure solve, we'll simply subtract the mean pressure from every pressure value. And so that way the average pressure is always pinned at 0. There's different ways to do that. Sometimes you'll see people specify a particular grid point, say this point is 0 always, and then all the other cells collapse around it. But here we'll just we'll just make the mean be 0. Okay, so here's what that looks like in order to code up these tables of coefficients here. We've tried to make the code look visually like these tables. So we have the 6 arrays B and the 5 pressure coefficients. The base point so JM means CP means coefficient of pressure, and JM means J minus 1, IM I minus 1, IP means I plus 1, JP means J plus 1. And so we're creating space for all of them. For the neighbor coefficients, their values are initialized, and then below, depending on whether we're at an edge or a corner or an interior, we'll modify these. Because the base pressure changes everywhere in the matrix, we'll specify that below, and likewise for B. So we have these 9 regions: interior, corner top, corner bottom left, side bottom, etc. And then we set up the array slice, which IJ pairs constitute the interior, which IJ constitute the corner, which IJ constitute the side, bottom, etc. And then we calculate B, and the coefficient of, in the interior we've already set the neighbors, so they're already done, and so we set the base point here, CP. And then for the corner bottom left, B is copied we directly copied it from this equation and then edited the two values that corresponded to the faces on the east and west. Or sorry, the corner bottom left, this would be the west, and the south values. So, and then we have to adjust the base coefficient. Instead of 2h and 2h, we just have 1h and 1h because two of the neighbors are missing on the corner. And then likewise, the two neighboring coefficients are 0. So we're just literally, the code is paralleling the tables that we discussed previously. And we do that for all of these points. Once we've got these as matrices, we reshape them into our one-dimensional arrays. So B, and then our coefficients. And then the A matrix will be diagonal. And it will be diagonal because at any point it has two neighbors. So you're going to have the main diagonal of the A matrix will, for this picture, have the A matrix will be 16 by 16, and the main diagonal will be CP for each of the main cells. But then every cell has a neighbor to the right and a neighbor to the left, and so those will be the CPIP and CPIM, and then this would be CPIJ and this is CPJP and CPJM, and each of those, these are shifted 1 to up 1 in the diagonals. This is shifted down 1 in the diagonals, and then the J values are shifted NX to the left and NX to the right. So we have to set that matrix up. And here we do that with A equals diags. And we've got the J minus 1, I minus 1, 0, I plus 1, J plus 1 in locations minus NX, minus 1, 0, 1, and NX. And this is a sparse matrix, so we're using a sparse matrix constructor here. And then once we've got the A matrix and the B array, we can simply solve it, spsolve, sparse solver for A. AP equals B, and that solves it. And then we subtract off the average from every value. Now that we've solved for P is a one-dimensional array. We want to reshape it back to the shape of our two-dimensional grid. So we reshape it. So we shape from 2D to 1D, then we solve, and then we shape the answer back to 1D and return the thing. And that's the pressure solver. Now, this solver isn't very fast. It's meant to be clear, not fast. Given that A is a constant matrix, for example, we can do, we could compute the LEU decomposition of it, and every time step we would have a faster solve because we've already got A decomposed into L and U. Okay, finally we have the driver and integrator. So the first thing we do is call the user specification function, set the grid and time variables function, and then we step in time. So when we step in time, for every time step we get HU, we get HV, and then we solve for the pressure. And then given the pressure field, we advance the explicit Euler method for the U momentum and the explicit Euler for the V momentum. And using array slices again keeps us from needing for loops. And that's it. This is the whole solver. Not so bad, right? At least the driver. There's all kinds of details in the functions above. Now, for convenience, we'll interpolate the U and V grids from the, we'll interpolate U and V from the U and V grid back to the P grid. So big U and big V are interpolated back to the P grids. They're all in the same spot. And then we can compute the velocity magnitude and the corresponding total kinetic energy on the domain, and we'll store the total kinetic energy on the domain just so that we can get a sense for the approach to steady state of the solution. Okay, once we've got the answer, we can plot it up. I'll leave the plotting details to you. but for the particular parameters shown, we have, you can see the streamlines here, and you get some nice separation. They're colored by the velocity magnitude. You can see the pressure field. The pressure kind of peaks in this top corner. The setup I have here is the top lid moves to the right and the right side is moving upwards. So you get this high pressure zone in the top right corner and a low pressure zone here in this other corner. And anyway, you can see the kinetic energy trace, the total kinetic energy in the domain, and when it's flat, you're basically at steady state. Okay, so that's been a lot of work. I hope that you enjoyed it. Hopefully this has given you some insights into how to set up and code a simple CFD solver from start to finish.